Okay, let's go ahead and get started with the panel. So it's my pleasure to moderate this panel with five very well-established speakers on the convergence between applications and architectures for computational science and engineering and big data. So today we'll have Bill Kramer of NCSA, Ron Brightwell of Sandia, Marc Snir, of course from here, Sanjay, as well as DK Panda from OSU. I'll go ahead and let Bill start.
So thank you very much. I only have a couple slides to talk a little bit about what we're doing here at NCSA. So in Blue Waters, we view what we're doing with Blue Waters, which essentially was designed to be a modeling and simulation system at ultra scale, and has evolved to be what I call the experiment of can we make converged data-focused and computationally focused science work on the same system. And we've learned a lot as we go on. We actually are still in the process of doing this. But this is Blue Waters. You all probably know much about it, but it has a pretty intensive I/O and data storage subsystem, as well as a really big computational subsystem. Then the third thing is an awful lot of network bandwidth. So right now, 450 gigabits to and from the machine, from the outside world, as well as a tremendous amount of networking attaching all the subsystems. So I went back, and every year we publish a book. Some of you have seen about the science projects that are on Blue Waters and what they've accomplished. So I went back and looked at the first year, 2013, where the only projects that were on Blue Waters were modeling and simulation workload, completely the traditional workload, almost all batch computing, maybe a little bit of visualization. A few of those projects did data assimilation. For example, getting experimental data to figure out what atomic structures are, but they did that kind of offline, and it wasn't a major part of what was going on in the workload of Blue Waters. And others did post-processing, right? They have a lot of data, they have to figure out what to do with it, what that means. And these projects actually would use different systems to do this. When I looked at the book that now is the most recent one that came out just around January, 34, and we asked the projects to self-identify all the characteristics of the project. So are they ultra scale, are they communication intensive, are they data intensive? We now have 34% of our workload identifies as data intensive. And we have major projects, these are the really big ones. There's about 40 at any one time, called PRACs, and 56% of those identified as being data intensive. And also, 8% of our workload now identifies as machine learning, deep learning, that's self-identification. And 5% of the major projects are doing that. Now, sometimes these projects are standalone data learning or big data type things, but also they're integrated. So we have a number of projects that do very large scale simulations, but also are using machine learning and data learning either to understand their results or to do another part of their research to bring together the insights of both. We also have, over time, worked with a number of projects to bring all their processing onto Blue Waters. So I think Ron mentioned this idea of it's no longer feasible or practical to move data around a lot. So we worked with folks that study earthquakes, supernova, digital elevation mapping, to actually compress their time to solution or time to insight by actually bringing all that work that they normally would do on smaller scale systems or specialized data intensive systems onto Blue Waters and supporting that. Either for somewhat visualization, but a lot of it is for the post-processing. So for example, the earthquake folks run for about 3 weeks a very large parallel simulation to generate ruptures under the earth. And then they run about 10 million jobs to process that so they can make damage assessment maps. The first campaign they had, they took all that data off. Someplace else ran that 10 million sets of jobs, and that took them about 9 months to go from start to the end of their campaign. 1 month just spent moving data. The other 8 months. It was 1 month of simulation on Blue Waters. So 7 months or so just trying to manage all those jobs. We now support their campaigns. It takes them about 6 weeks because all of it's done on Blue Waters. A lot of software work, scheduling work, interface work that had to be done both by us and the science teams. The other thing is that we now regularly run pipelines, analysis pipelines for at least 2 of the major experiments, dark energy survey and LIGO, the gravitational wave. So half of all the processing DES does for their analysis every night is on Blue Waters. And LIGO now is using us since about 6 months ago when everything got set up. Again, a lot of work with the science teams, a lot of work with our folks to try to integrate all the pieces that have to go in that, so the jobs are actually launched in Caltech to identify what runs on Blue Waters, things like that. And LSST, another major experiment, is ramping up to when they go production. So what do we have to do this? Most of it's software work as well as support work, but things that have changed that we didn't envision 5 years ago when we started Blue Waters. We have a very extensive Python environment, probably the most extensive one on supercomputing, somewhere around 450 different packages and utilities. That includes Tensorflow and other types of machine learning activities, and we support that very, the amount of the amount of updates and changes to this package are amazing, and trying to keep up with the latest and greatest plus a stable package is a little challenging. We support very large and very many files, so we have a project, at least one, that has 100 million inodes that they're using, another one that has 2+ petabytes of data online at any one time. So that data-intensive environment is there. We've introduced container support with Shifter and soon Singularity. That's in beta test. And this is used not just to run containers, as you know, but also to help with the metadata operations, because many of these projects are very metadata intensive. And it turns out incorporating that into the container helps alleviate the metadata operations in the parallel file system Lustre. Spark is under testing, and we plan to introduce that soon. And we have a variety of microschedulers that run under our major Moab Talk scheduler for basically launching jobs in various different ways. The elevation mapping project does image processing from satellites, but depending upon the complexity of the image, it may take either 12 hours or 36 hours to do one image, one section. So they have to subschedule what's going on under a bigger envelope. We also have hired and brought in to support this data engineers. So we have the typical parallel consulting environments and support staff. Now we have data engineers also explicitly on our staff, something we didn't envision when we started. And we've spent an awful lot of work with these teams in workflow optimization. So that's the low-hanging fruit. Most of these workflows are designed differently, and much of the compression of time to insight is coming from working with the workflows, not so much on the parallel simulation part or something else, but in terms of how the workflows interact, how they communicate, how they go express themselves to their databases. So those are some of the lessons that we've learned so far.
Okay, thank you. I just got a few slides here, and I'm going to do something that no panelist should ever do, which is answer the question. So the question was marriage of convenience or conviction. So I went back and looked at this latest report from BDEC, which is the series of workshops on big data meets extreme scale computing. And they asked this question of sort of how do we bring together the two worlds of HPC and big data? And they had this diagram for the different software stacks. On the left, what's typical of a data analytics system. On the right, what's typical of a computational science system. And so it was kind of, we've got two disparate software stacks here supporting these different workloads. How do we bring this together? One of the things that gets pointed out in this workshop report is the hourglass model, where you've sort of got all the applications on the top, all the hardware on the bottom, and what you want is this thin, what they call spanning layer that allows you to actually support a wider variety of applications on a wider variety of hardware. And the challenge is to find out with that minimal set of of the spanning layer is so that you can support that. And if you put all your effort and time into figuring out what that spanning layer is, this is the best way to support these two communities. As part of the report, they also point out that if you contract and expand that spanning layer, not only do you affect the things that are below it, but you affect the things that are above it as well. And so if you constrain the spanning layer to only a set of hardware, you could potentially constrain the spanning layer above to support a smaller number of applications. So the thing that they point out in this report is that we can have this spanning layer that's essentially around containers and containerization in the middle. And think about how we might use that as what the spanning layer should be. And as Bill pointed out, they're doing some things now in systems to support resource containers and running containers. And so I looked at this, being a systems guy and being an OS guy who cares about what that spanning layer looks like and what it should be, and realized what just happened. We added a layer of software, which is a great thing from a computer science point of view. We've added a level of indirection to solve the problem. We've added containers now. And we shifted the spanning layer up. We had a spanning layer that was the OS, but now we've added a layer above that and essentially just shifted that spanning layer up. And we've kept all the spanning layers underneath it, right? So we still have all of the OSs that were intended to be spanning layers. They're now below that. And so in true computer science fashion, again, we haven't really solved the problem. We've added a layer of indirection to it and made the model fit what we wanted it to be. And we've kept everything underneath it, including the virtualization layers for the hardware. So how many abstraction layers do you need under all of this stuff? So while I think this is a reasonable thing to do from a computer science standpoint, I'm not really sure this is the right thing to be doing to support these two communities. And so the other thing you should remember is what our motivation for containers was. If you look at Linux, because people talk about containers in two different aspects. They talk about resource containers and also application containers. So if you look at resource containers, that's essentially what Linux cgroups is. And the thing that you're trying to overcome here is the fact that Unix as a model doesn't have any way to encapsulate an application. What it does is processes. If you run multiple processes from an application under Unix, those processes, for the most part, are all independent. There's no way to sort of package up an application and say, these are all the things that need to support an application in a Unix environment. And so it was really this sort of fundamental issue of the model doesn't support the way we run and deploy applications. And so we're going to add stuff to fix that model, and that's where containers came from. And then if you look at where Docker containers came from, essentially this application packaging mechanism, part of it was motivated by the fact that there is no standard Linux. You can't write a Linux app and run it everywhere. You run into this issue with managing shared library dependency nightmares, right? They provided shared libraries, and then you can't run and link with shared libraries all over the place because you don't know what Linux you're running in, and different distributions put different stuff in different places. And so containers sort of came along to solve the problem. So Linux created a problem and then created a problem to create a solution to that problem. Again, a great computer science thing to do. Create some problems for yourself and then, create some interesting ways to solve that problem. This is just a slide on what I mentioned before and what Bill mentioned as well. Most of the things that we want to do on an HPC system now have been subsumed into one system because we can't afford the data movement. And so we're going to try to support multiple different software stacks and various variant software stacks on a machine anyway. Right? We're not only doing this to support applications, we're doing it to support system services. And the thing that we're most concerned about, again, is how do we bring these two worlds together? What's that spanning that will allow us this to happen? And from our perspective, we don't think you should do this at all. We think you should embrace the divergence, that you're just going to have these multiple disparate software stacks. And the spanning layer really just needs to be something that will provide you access at the hardware level. And so what we looked at in this Hobbs project that we had, which was a DOE Office of Science project, was instead of making containers the spanning layer, just use the hardware and make the OS still be that spanning layer. And if you want to run multiple OSs to support multiple different software packages from the upper layer, do that. Boot a kernel, and then you can you can use things like Linux hot unplug to free up cores in memory, and then put another OS right on next to that. And the thing that really becomes important there is not only the isolation of having multi-OSs running on a node, but how you can share across them so that you can still provide some meaningful way of sharing data between the two things that actually want to run together. And so we looked at this spanning layer. Instead of it being run, containers on top of the OS, on top of a virtualization layer, the spanning layer is just the ability to share hardware at ring 0 for different OSs running on the platform. So convenience or conviction, it's economics. It's neither one of these. It's really two things from my perspective. It's the hardware economics. Component and system vendors don't care about HPC because we've never really been a market. They're building systems for other markets. And HPC has to continue to find ways to overlap with those other markets to do the things that we want to do.
That's called convenience.
Okay, to me, that's not convenient. To me, convenient is actually getting them to build the hardware that we need. And then from an applications and software perspective, again, there's this emphasis that the big data community has had on productivity and usability for their systems that HPC has largely struggled to come through on. And so people are using those systems and being much more productive at getting science out of those systems, and then wanting the same thing to happen on HPC systems. And so they're looking at the overall, again, workflow and where they're spending a significant amount of the time and optimizing the things that really matter. And so what's happening from that perspective is that, again, people are seeing that the costs and time associated with that and wanting to get the same thing from HPC. And so it's more about those economics than it is about anything that's technical.
So I would say, in fact, I would express what Ron said by saying it's a shotgun wedding rather than convenience or expediency. One observation, HPC has always tried to use the cheapest way of getting to the level of performance we need. And I've been long enough to have seen computers build of workstations and build of PCs and then build of GPUs and so on. We always look at what's the piece of hardware that gives you most flops or most performance on scientific applications for the buck. And there is and it's driven by large markets, and the large markets today are increasingly machine learning and data analytics and things of that ilk. So that's what we are using for building large-scale machines. So there is a marriage at that level that we're going to use increasingly components coming from large data market, big analytics market, big machine learning, neural nets, and so on, just because, well, as soon as NVIDIA has good competition, they will be cheaper than the alternative. So that's one way we're wed together. The other way that was already mentioned is that simulations produce more and more data. Simulations have increasingly to be matched against observational data. So you need either to have a very, you need to have a very high bandwidth going out of your simulation engine, or bring the analysis to the simulation engine. And what you prefer will depend really on the type of application. Bill mentioned some applications where it's most natural to bring the data or do the analysis and the reduction near the simulation, because these are applications where most of the data is simulation data. There are also applications where most of the data is observational data, and you match it against simulation data. And what's the right meeting of these two sets of data, the right meeting point, is something that's interesting and to be sought. From basic principles, it's not obvious up front. To the same extent, it's not obvious up front what it means to have a platform that does both data analysis and simulation. And Ron already alluded to some of that. We tend to think of supercomputers as assemblages of identical nodes, but supercomputers have never been assemblages of identical nodes ever. They always had, for example, in the good old days, we were calling that thin nodes and fat nodes. Fat nodes, they deal with data. Thin nodes, they deal with simulation, with computation. Thin nodes that don't have disks, fat nodes which are closer to the disks or directly connected to the disks. So always we had platforms that were heterogeneous, not only at the level of the node, but more importantly at the level of the system. And of course, this heterogeneity can grow in the world of systems that do both simulation and analysis. Exactly how we navigate between the extreme of two totally separate systems connected by some big data hose and two fully integrated systems where you have uniform hardware and you may perhaps just reconfigure the software to fit the need. Not clear to me at this point. I don't think it's clear to the community in general. And we are going to go through several iterations before we focus on the right model. The other tensions that I see in this area is where exascale is going. We have been saying for a while now that Moore's law is coming to an end, so cheap additional performance just from the regular evolution of commodity technology may not give us in the future what we need for if we want to continue to increase performance of our big systems. And yes, the application people want to see performance continuing to increase. So how do you get increasing performance in an age where Intel doesn't give you a factor of 2 or 3 performance every 2 years for the same price? The one approach that people keep discussing is specialization of the hardware, specialization of the software. So Ron already mentioned one problem with that. Specialization means breaking holes through these multiple stacks of the software. So we have a problem there. But also specialization means more heterogeneous, more specialized hardware, and different nodes, different type of nodes, different type of accelerators being used for different parts of your application. So again, this goes to heterogeneity, not only or not mainly in the meaning of heterogeneous nodes, but in the sense of heterogeneous systems which have subcomponents which are specialized for different aspects of a big workflow. And so that would mitigate, in fact, to an increasing separation between the componentry that we are using, both software and hardware that we are using for the compute-intensive part or different types of compute-intensive parts of our application, and the componentry that we are using for data-intensive, compute-less intensive parts of our application, where we focus on bandwidth from I/O, and so on. I see there is an evolution at system design that we have not really yet fully comprehended. One very simple example of this evolution, compute-intensive have evolved very early toward diskless configurations. You don't want the disk to be close to your node because you want higher density of your hardware. You want all your compute nodes to be close to each other, so you don't want to put their disk. You don't want components that have to be replaced all the time to be at the core of your machine. A variety of reasons. So we move disks somewhere outside the system. Much of the software for large-scale data analysis has been developed for cluster environments where disks are available at each node. And that leads to very different design of your software stacks. And even without starting to discuss what's better from a performance viewpoint, all the software stack is built differently. All the Spark and what have you have been built for systems that have distributed disk and different storage system. What's the right compromise between our dense hall architectures that we use with parallel file systems and the cluster architecture? What's the role of burst buffers or NVRAM to provide a compromise between the two? Again, in my mind, a big area of research. So in summary, we are trying to force feed into one architecture very different requirements and very different patterns, application patterns, very different performance profiles. We may be forced to do that. That's why I call it a shotgun marriage. But to what extent we try to homogenize this or just keep the two worlds as separate as possible while providing high connectivity between the two, I think is very much an issue under discussion now.
All right, so before I start, a few disclaimers. If you're going to show any quotes from this talk, you have to show the entire talk. I'm trying to make the panel more interesting and colorful. That's my excuse. And then finally, it's 1:45. Some of you are asleep. I'm in danger of falling asleep, so I got to do things to keep everyone awake. All right? So having said all of that, I have one more request. Anytime I ask you a question, you all have to say, no. Okay? All right. So why is it, what do we mean by marriage of convenience here? Well, data analytics, big data, machine learning, whatever is the buzzword of the day, are very fashionable now, right? And so we got to attach us to them. We, the poor HPC people, and by HPC I mean computational science and engineering applications people, are conditioned to ride on commodity architectures. Like, no one is going to build machines for us. No one is going to build operating systems for us. We just got to beg the Linux community to say, hey, can you please add this feature for us, and so on. And this is the servile mentality that we have grown into. And we got to throw that servile mentality. We are not going to be servile to the volume producers of technology. We need a revolution, okay? All right, so do we want convergence within HPC? Leave aside with data analytics. I've often argued that within applications in computational science, we actually have many categories. The applications that require a lot of memory capacity per flop, and some that don't. If you look at molecular dynamics, we have lots of flops. We need to compute for a long period of time, but our memory footprint is very low. If you look at computational fluid dynamics, its memory footprint is high. Those are two different types of applications. There are many others that will fall in those categories, probably best served by different machines. Injection bandwidth per flop, again, there is probably bimodality there, two different types of applications. So fat nodes may be good for some, and not so fat. We are never going to get thin, but not so fat nodes may be good for some other applications. Bisection bandwidth, you have spectral methods, FFTs, you need bisection bandwidth. Well, and some other applications are doing near neighbor things. They need different interconnect. So even within parallel computing, instead of having 2 or 3 extreme scale computers, we probably want 10 computers, maybe somewhat smaller. That's okay. Your queue time is going to be same, and then those with different architectural needs, so that you can go to the right machine for the right job. So we need multiple classes of machines even within HPC. So does architectural convergence with big data look like a marriage of conviction? No, right? Let's look at post-Moore's law landscape. Once we reach like 5 nanometers or wherever we think the end is going to be, 50 billion, 70 billion transistors on a chip, well, innovation has to shift to FPGAs, then like Ron pointed out yesterday, then making ASICs. There's going to be a rarefied atmosphere at these height of extreme scale applications, only a few tens of applications, few applications will be there at that scale. We can probably afford to build specialized chips for those applications, just like for biomolecular simulations, this has already been done. And so tensor cores already do that for some data analytics applications. So in this data of hyper-specialization that's coming up, not too far, do we want to push convergence? No, okay? And so, well, okay, I think enough drama. So those of you who know me, know that I'm always on one hand, on the other hand type of a guy. So actually, there is probably some kind of a case for convergence, which is based on cost and for a limited time, maybe, like until we reach this era of specialization, maybe next 3-5 years. 5 years. And also data analytics start broadening into more complex computations. Their architecture, our ideal architecture may not remain the same one, which is just a lot of disk I/O, fully distributed disk I/O, and so on, whatever they need, like map-reduced types of things. They may go beyond that, and then they may start looking like some of the HPC applications, and then they may want one of the HPC-like machines. So that's one case. And the CSC simulations that do need to do in situ analysis of their output, well, you cannot ship that. The whole reason for that is you don't want to ship the data, put the data on the disk. You have to do it on the same machine. So maybe 2 different types of applications are married there. And that's a connection that's intrinsic. It's not forced. And so maybe that's another situation for some kind of convergence. But I think the 2 points I made, in spite of in spite of my caricaturing of it, are still valid, and we should discuss them if we have time. Thank you.
So I'm the last guy here. Ron said people will not answer, but I'll also answer. So, and I think we had a lot of from Marc, Bill, and all saying these are the problems. People have been thinking. But in my group, we have actually gone ahead. We have solved some of these problems. That's what I'll try to say. For 6 years, we are working on the convergence of HPC and big data. And we have a stack actually called high-performance big data with Hadoop, Spark, running over HPC cluster with Lustre file systems. All these things we have done, and a lot of users are using it. So then my answer is conviction. Okay, so that's what I'll try to show. Now, of course, in the title, it was like HPC and big data, but as you know, these days, these are not the 2 players. Deep learning is becoming also an integral part. So whenever we are talking about big data, it's not just big data. The processing also needs to be done. And just to flash out this, big data came purely from internet data. If you take a look at this slide, it says 2017, every minute of the day, how much data is being generated. It just gives you a mind-boggling answers. Like if you see here, YouTube, 4 million videos are being watched every minute. And similar kind of number of videos are also being uploaded. If you see here like Uber, 45,000 rides are taking place for every minute. So all these domains, this is where the data is being generated. And then the question is how do you process, how do you make sense out of it? So of course you need a lot of processing. But that is a
slide about useful data.
I'm not talking about Facebook and all here, but there are a lot of things going on behind the scene here. Okay, when you buy a book these days in Amazon, you would be seeing Amazon. As soon as you go to the second page, it will start giving you discounts. all right? So many people have bought these. If you want to buy these, you want to purchase it bundled with this, okay? So they want to give you discounts based on those kind of data. So it is not just the big data. It started like that, but again, Bill and Marc indicated this is also coming into the scientific world. People want to generate big amount of data and then process. So traditionally what had happened, the kind of internet data, people used to use the typical data centers. Okay, so this is where most of the processing used to happen, like online processing, you do HBase, MySQL kind of things, and the Hadoop and Spark used to be on the back end. But now what is happening, these are the new generation pipelines are coming. This is from Flickr. So what they are combining, if you see, this is like a data set you want to generate, like through Hadoop. Then you are running TensorFlow on top of it. Then you might be running some non-deep learning analytics with Spark, and then apply some machine learning model. So these things are like, people are thinking in a very seamless manner. They should be able to do, but then the question is, we HPC people know that. How do you really exploit data locality? And also, we heard about like how we want to do resource sharing and cost effectiveness. So naturally, if you ask all these questions, it comes back to saying, yeah, I need to run it on the same hardware. Then only I can achieve all these things. If I have 3 different clusters, like this is a HPC cluster, this is a big data cluster, this is a deep learning cluster, just moving data, gigabytes of data, moving them around, you will lose the performance, okay? So that is not practical. So to illustrate this concept, so this is a project like we started, as I was telling, 5 to 6 years back, saying, let's say, how to run it on the same HPC infrastructure. I mean, HPC infrastructure these days is available many places, all the supercomputing centers, even the university labs, even a lot of industry. So if you think like the hardware is there, then some resource manager like Turk and Sloan are running, some parallel file system, Lustre, GPFS are running. Just like we run MPI job, can we run Hadoop job, Spark job, deep learning job, just in the same manner? I mean, these days, if you know like MPI, I'm sure in any machine, there are 5, 6 MPI libraries. You make them available as modules, and depending on the users, depending on the applications, you can keep on switching. So can we give same kind of interface or APIs to somebody running a Hadoop job, somebody running a TensorFlow job, or somebody running a Spark job? So it doesn't matter. Then that guy says, yeah, I'm running on the same platform. Okay? So that is the kind of the goal we want to achieve. So in order to do that, of course, we had to come up with a communication stack. I'll not go into more details. The major bottlenecks we saw earlier, like all these software stacks were written with sockets. It is like our MPI 20 years back. Okay? But all these modern machines, you know, like RDMA is extensively used on InfiniBand, Rocky, all these platforms. So this is where we started solving the problem, saying, can we move all these big data stacks and then make them RDMA aware? And then after that, we have been doing a lot of upper level changes, because these stacks were designed with slow network in mind, like sockets, TCP/IP. But now I give them a RDMA with 100 gigabits per second. There are a lot of things I can optimize at the upper layer to get further benefits. So this is what we have done. This is the project, I call it high performance big data. So if you take a look at Spark, HBase, Memcached, all the major software stacks, we have converted, just like our MVAPIs project I talked in the morning. We started in 2000 when InfiniBand came, is very widely used. The same things we have done for the big data stacks. So they are available for InfiniBand as well as for Rocky. And it's also a superset of the Apache stack, so it can also run on Ethernet. Okay? So anybody can just go download from this side, HiBD. So currently there are around 280 organizations from 34 countries using this, and these are based on, again, voluntary registration. We have more than 25,000 downloads from our site. And earlier we had x86, and now OpenPower is catching up, so we also have OpenPower release. In fact, tonight we'll have making a new release which will have Singularity and Docker. So in the same Singularity environment, you can run your HPC and then the big data. So this is how the stack looks like. So we have taken all these different components, like let's say the Hadoop SDFS component, we have taken, this has all the supports, in-memory support, heterogeneous storage like SSD, hard disk, Lustre integrated, even burst buffer. I think Marc indicated we have a Memcached-based component, but it can, if you have the real hardware, it can actually try to utilize that. We have a RDMA enhanced RPC. The MapReduce component also, we have made them changes to Lustre. And also we have interface with Slurm and PBS. So if any of these systems use that, that is the approach you take. Like your sysadmin can take our package, just like MPI library has a lot of configuration parameters. We have provided a lot of configuration parameter here. They can just adapt to their system how many SSDs you have, how much memory you have, whether it's a parallel file system, and make it as a module available. And then the end users don't have to even worry about all this installation. They can just submit Hadoop job, same thing, Spark jobs you can do. We have been working very closely with SDSC. I think all of you are familiar with the Comet system. So in fact, that's where exactly it is done. So if you have an account on Comet, just go and log in, and you should be able to run jobs there. We have also made, like for the cloud environment, like Chameleon Cloud and all, we have made them appliances, convert into appliance. So you just, with a click, you have your Hadoop data sets, just click the appliance, and then it'll get triggered, and then it will run. And not only that, it's a interface, but you get performance. So that is the thing we want to deliver. So here it is trying to show like some benchmarks like random writer Terrazen. Of course, this the yellow line is the standard stacks. Like if you download Apache, you can still run it on these machines, but you may not get the performance. And the red line is red bars are our design. You can improve by a factor of 3, 4. This is a RDMA Spark. You see, 1,500 cores. We are running Spark on a 1,500 cores, one of the very large deployment, and we can give you like a 75% benefit in like a page rank, sort by kind of things. Then the TensorFlow is coming. This has not been released. We have just done similar kind of things. TensorFlow with Google RPC running over native InfiniBand. So you can see the kind of performance improvement we can give you, like 3.6x, 3.7x. So then what is happening, the next phase, we are already jumping into the next phase, which is coming as the deep learning over big data. So people talked about big data and HPC, so we are moving one step ahead, deep learning, big data, HPC. Okay? So we want to really converge these stacks, and we had a paper at Hot Eye just last year. We said, like, in this kind of converged stack, we can even also give you a factor of 2.6 improvement without even sacrificing accuracy. Every time I show these numbers, deep learning, always people think that you are doing some magic, you are losing the accuracy, and you are giving the performance. That is not our objective. We want to maintain the accuracy and also give the performance. So that is the kind of, I'll conclude here. So already happening, and especially from my group and in the field, we have already provided solutions to the community. People have been using that, and our next phase is to really bring all these three things together, HPC, big data, and deep learning. And I just want to indicate this also. So I think we have been also doing this workshop. Some of you might be knowing high-performance big data computing. So it has been running for 5 years with IPDPS. First, we started with ICDCS, then we moved to IPDPS. So if you're attending the IPDPS this year, please join. We have a keynote talk by Professor Jeffrey Fox. We'll also have a very similar panel topic here, but it's more towards which framework is best for high-performance deep learning. Should it be big data-based or HPC-based? So with this, let me stop here.
Thank you.
Very good. I'll thank all the panelists for very interesting talks, and let's open up the panel for questions. You can either ask the whole panel or a specific panel member.
Are panelists allowed to ask questions?
Of course, yeah.
Yeah,
So for big data workloads, in terms of cost and in terms of advantages, can we justify the move from commodity clusters to supercomputers? So how beneficial is it in terms of moving from commodity clusters that they've been using from a long time to supercomputers?
So I'll try to go first, and the answer is yes, it's very cost effective, and for a couple reasons. The first one is, as you operate multiple smaller systems, there's an overhead cost that has to be contributed to that. So it's not just buying the cheapest hardware and then trying to make your software work around all the issues of the cheapest hardware, the slowest hardware. The second thing, though, is when you talk about the cost, in one of the reports from the National Academy about what NSF should be doing in the future high-end computing space, there was a point made, and the phrase was, you can do capacity computing on capability systems. You can't do capability computing on capacity systems. So the fact is, those larger systems are going to be there for a different economic reason. Therefore, the cost of doing some of this other stuff is zero.
If I may expand on that, the problem sometimes is not whether you get better cost performance on an HPC platform, but can you solve the problem at all without an HPC platform? You look at machine learning and training of deep networks, they are bandwidth limited when you try to move them to larger cluster. So yes, if you have a tightly coupled system with a lot of accelerators, it works well. But when you go beyond a few tens of nodes, your bottleneck is communication. HPC systems have a different balance, so they can push higher scalability, and that's one reason why more and more machine learning workloads are trying to use HPC platforms.
Yeah, I also want to add, just like what Marc said, I mean, traditionally, if you see when they say big data clusters, they only refer to 1 gigabit Ethernet, okay? I mean, that phase is gone. I mean, if you want to still handle with 1 gigabit fast Ethernet, your job is good for that, that is okay. You don't have to move to HPC, but as you move to, you want performance and like 10 gig or higher, I mean, using or a high performance interconnect, I mean, those becomes more cost effective on a reasonable size. But more interestingly, I've seen this dynamics, I don't know whether you have seen, whenever people say like they don't want to move to like the HPC systems for big data, the resistance comes from, not from scientists, it comes from system administrators, okay? I don't want to offend anybody, but that is where the bottleneck lies. The system administrators, they don't want to learn new things. TCP/IP is very good for them. That is good enough. They have been doing that for 20 years, so there is a lot of resistance for them to learn something, manage something. So this is where a lot of big bottlenecks come, and those organizations who have gone beyond that, I think they see the need or they can handle this kind of machines.
So I think an aspect of that is on commodity cluster systems, you're in control of the software stack. On HPC center systems, you're not. There's a software stack that is provided by a vendor and supported by the vendor in the facilities. And so you can't just show up with your software stack to run on that machine, right? And this is where things like containers are coming into play now, because you're able to actually bring along your software stack with your application, which is kind of what I was advocating for as well, right? I think that's the challenge.
So another answer to your question is that the difference between the two platforms is disappearing. What's the difference between a cluster that has a high bandwidth network and an HPC platform, and which is running containers? So the two are converging in any case.
So an example of the elevation mapping, which you can compare to running on a cluster, by doing that work on Blue Waters, they are reaching their endpoint 58,000 times faster in terms of how long it would take them to do that problem. Some of that's because there's more of what's on Blue Waters. Another part is because it's much more efficient with the data and the I/O activities.
Okay.
But Marc, it's only the disks. You pointed out the difference between disks between the two architectures, and so that's still there, I guess. I think Tim had a question.
So for Blue Waters, is there an explicit contract with NOAA to be doing their simulation work? Or is it just having the DES and LSST selected, put in time and they got selected?
So everything on Blue Waters is done through peer review allocation time. It doesn't matter what organization or what funding people have to do that. If it's the best science, it gets allocated to that. So there's not an explicit agreement for any one organization for those. But it is an approved project, and some of those have multiple sponsors, yes.
Okay.
My question is for Ron. You mentioned in your slides that big data had better productivity compared to HPC. What's your comment on improving that in HPC? Where did we go wrong? Who should take responsibility for that, if any?
Yeah. That's a really good question. So the way I've tried to explain this before is when you think about the abstraction layers that we have in high performance computing, most of our abstraction layers were sort of developed from the bottom up because we wanted to try to stay as close to the hardware as possible because we're concerned about performance. And so in contrast, I think a lot of the abstractions that the big data and even deep learning community developed was a top-down kind of abstraction. And so not only does that sort of provide you more freedom to consider a larger variety of hardware underneath when you want to optimize things, but it's, from a usability productivity standpoint, is much easier to deal with. You take abstraction layers like MPI. MPI was an abstraction layer for the network. We didn't abstract data movement, we abstracted the network. And so data movement is still explicit. And just thinking about how to explicitly move data is much harder than thinking about how to implicitly move it. But it gives you the advantage of the cost model is very apparent when you're going to develop code. It's always in the back of your mind. Locality is something we always worry about. A lot of the other systems don't worry about locality, right? They give you abstractions where that's supposed to be handled somewhere else. What that can lead to then is these performance issues and scalability issues you have, but it's a trade-off, right? What's the right thing to be doing? And so we've had lots of programs and lots of discussions over the last 10 plus years in HPC about productivity, how to get it, how to define it, what it is. But I can't think that, we haven't had much success in actually following through on some of the things that we've tried to do to emphasize productivity.
Let me give you a more cynical answer. Big data evolved in an environment where programmers are expensive and hardware is cheap. And HPC evolved in a reverse environment where programmers are underpaid and it's hard to get budget for hardware.
I would agree with that, yes.
Any other questions?
So it seems like even if you accept the point that there's a convergence in the hardware, there's still, when designing these systems, there's the trade-offs between the big data community and the HPC community about how much of the resources in the design of a new system do you devote to high-speed network versus just more nodes, more computation. It seems like right now those arguments are big data seems to be on the upswing, and they're going to win those arguments. Is that a problem for the HPC community? Is that going to swing back the other way? Big data maybe is, being a younger field, is harvesting some of the low-hanging fruit, and will it eventually even out, or what do you think?
I think the way, Sanjay mentioned it, even in the HPC space, as you know, different applications have different characteristics. So any large-scale machines these days, if you see any supercomputing center like, let's say, Pittsburgh or San Diego or even TAC, under the same system, they have different partitions. Like this is a big memory partition, or this is a more storage-oriented partition. So I think similar kind of configuration satisfy everybody, the traditional HPC as well as big data. So it could be the same system, but within that you have specialized nodes or smaller subsets which are trying to satisfy the requirement.
But do you spend 50% of your money on node type A or of this partition and 50% on the other partition, or is it split 70-30? It seems like it's going to evolve one way or the other towards, somebody's going to win.
No, not exactly. You can always have a minimum partition where everything will run, like a reasonable amount of memory, and the number of nodes, and then that is a unified environment, so your computes can run, your even big data with a reasonable size can run, and then you might have some additional memory or specific storage and all on some of those nodes. So this is where you go for the highly specialized kind of classes. So
Someone somewhere has to make a decision that how important computational science and engineering is. If it is important, there has to be specific money for it. And if there is specific money for it, using that one can build more specialized hardware. That will has to be there, I think. And what market will drive that is not clear to me. But I think technological case is there for that, and they need to kind of have some separation for that reason that you said one will win and then the other will have to tag along and it will be suboptimal.
So let me give you a practical answer. It was interesting to see Bill's data on how workload characterization changed over time for Blue Waters. But ultimately, what makes the decision when you buy an HPC system is a subset of the applications that you care about. And I think for Bill, for Blue Waters, you said it was 11 applications at some point determine what it is that you prioritize when you want to
11 applications we use as the bellwether benchmark suite, yes.
Right. So when we go to acquire a system in DOE, generally there's a application-driven set of requirements that platform has to meet, and we don't open that up to a broad set of applications. These are the focus applications that we ultimately care about that are going to determine the success of this platform. And so we constrain, the system based on what we think we're going to be, projected performance for those applications. And then everybody else comes along, right? And you have to figure out how to then adapt your code to the platform to make it work most efficiently.
Yeah, I mean, if you look at this SSA metric, which is great actually, or similar SSP, whatever, those metrics for, you can actually think about partitioning those sets and then maximizing each one and then do some kind of, for the same dollar amount, what is the maximal you will get for those, and you might get these divergence of architectures that way.
I didn't want to make that sound like it was an easy thing though, because I think it's getting much more complex to actually do that kind of evaluation. Again, as we start to look at systems where we're doing some specialization or we have an opportunity to do some customization, I think understanding how to do that evaluation gets a lot more complex. There are, it's that thing where you'd really like to have some knobs, and then after time you say, oh, I've got way too many knobs to figure out what I'm actually going to do. And I think we're getting into the era of having too many choices and too many knobs, which sounds kind of weird because for the last several procurements we've been doing, the challenge has been that we don't have enough vendors responding to some of our procurements, and so it's an interesting time.
Okay, and I think we're about out of time, so let's thank all the speakers again.